So this is a walkthrough of the November 2018 paper 2 for IB. This is the paper we used for our mock, and we need to improve in places, so it's important you go through it really carefully. I'm going to do the entire paper. You can skip to the bits, the questions that I gave in the mock if you like, but here we go. Right, so the first question asks you to work out which is the limiting reactant out of iron and copper sulfate. So if in doubt, as always, as you know, you work out the number of moles of things. Now it's really straightforward to work out the number of moles, isn't it? If you've got a solid, you need to know that you can work out moles by doing mass over MR. So the mass is 3.26 grams, and the moles, number of moles, or the amount, is equal to the mass divided by the formula mass of the iron. So 3.26 over 55.85 comes to, where is it? 0.0584 moles. And again, I'm showing units as I'm going all the time, making it really clear what I'm doing, showing that the mass of the iron is this, and the moles of the iron is this, and the moles of the copper sulfate are this. So be really clear to the examiner so they can see what you're up to. To work out the number of moles from a solution, is volume times concentration, making sure volume is in decimeters cubed. So I've converted 80 centimeters cubed to 0.08 decimeters cubed, times by the concentration in moles per decimeter cubed, and that comes to 0.016 moles. And as they're a 1-to-1 ratio, the limiting reactant is the one that there's the least amount of, and that should be pretty straightforward to figure out. So copper sulfate is the limiting reactant, because that's the one there's less of. So just, I didn't give myself much space, but you could just write here limiting reactant. Okay, something like that. Next, you have to work out the mass of the copper obtained, which was, the percentage yield of the copper obtained. The mass obtained apparently was this mass given here in the question. So we need to work out what would have been obtained had we got 100% yield to start with. This is what we call our theoretical yield, isn't it? So to work out the theoretical yield, you first of all do, there's a couple of ways of approaching this, but work out the theoretical yield by doing 0.016. So it's trying to work out the mass of copper obtained. It's a 1-to-1 ratio, so it's just the same number of moles of copper sulfate as copper, so the N of copper is equal to 0.016, and then the mass of copper obtained is equal to 0.016 times by the formula mass of copper, which is 63.55, and please use the values in the data book here, it really does help the examiner, which is 1.02 grams, because mass is equal to MR times moles, and then you can work out what percentage 0.872 is of 1.02, so 0.872 divided by 1.02 times 100, and that comes to 85.5%. You could have approached it a different way and worked out the number of moles. This is by doing that times the formula mass of copper, and then working out what this is as a percentage of the moles obtained, right? Or that should have been obtained. So there are two ways of doing the same thing. Question 1b, very straightforward routine question. This is, so easy because it's just straight from stuff. So you didn't revise as much, some of you, for the mock as you will do your real exam. This is the kind of thing which should be absolutely routine. Everyone in year 12 can do it, and you should be able to too. But we work out the energy transferred to the water in the calorimeter by doing Q equals M times C times delta T. And as I warned you would happen back in year 12, and I warn my year 12 this year again, you need to know this is the mass of water, not the mass of the reactant that was being heated. So the mass of the water used is given in the question, because it's 80 centimeters cubed of water, so it's 80 grams. 80 grams of water used. Specific heat capacity is given to you in the data book, 4.18, and the temperature change is 7.5 Kelvin. And so the number of moles, the number of joules transferred is 2.5 times 10 to the 23 joules, which is equal to, we normally convert to kilojoules because in the end the delta H should be in kilojoules per mole. The delta H, of course, is equal to minus, because it's exothermic, Q over N. So it's minus 2.5 divided by the number of moles, which is the limiting number of moles from up there, 0.16. And if you gave the wrong answer there, I did take that into account. And so you do the energy transferred divided by 0.016. And that comes to minus 1.6. The raised written in the mark scheme is 1.6 times 10 to the 2 kilojoules per mole. Okay, I'm failing to squeeze it into the box because I'm printed out on a smaller size for some reason. So you can fit it easily in the box there, or you might have written that as not in standard form, and that would be just as fine, just as good. Right. Some assumptions. There's lots of possible answers to this. This is why hopefully these videos are somewhat useful for you. Ignore that for now. The assumptions you've made there. One is that, well, we're using copper sulfate solution. In fact, we're using copper sulfate solution, and it becomes iron sulfate solution. And we're assuming that the mass of the water is 80 grams when the volume of the copper sulfate is 80 centimeters cubed. It's perfectly reasonable to assume that the density of the solution is the same as the density of water. In other words, the density is equal to 1.00 grams per centimeter cubed. Okay, that's a perfectly normal and reasonable assumption. It's not completely accurate necessarily, but it shouldn't change your answer significantly. Another thing you could consider is that the specific heat capacity of water is what we're using is 4.18 joules per gram per Kelvin. But that might be slightly different in the copper sulfate, so we're assuming that it's the same as water, which is fine. Some of you wrote the reaction goes to completion, which is fine, and that there's some of you just wrote there's nice side reactions, but better if you make it clear that you're saying either the iron or copper sulfate does not react with other substances, but essentially side reactions is what you're getting at there. So there's lots of ways of answering that question. Now, loads of you struggle with the uncertainty question. So I've started it just to save myself a little bit of writing. The only uncertainty that's significant here is the temperature measurement. So we need to do some work with this one. So we have to determine the absolute uncertainty of the value calculated, the delta H we just calculated, if the uncertainty for the temperature was 0.2. So we've got to take our uncertainty for temperature and then transfer that to the uncertainty of the final answer. So the first thing to do is to work out the percentage uncertainty for the temperature. The temperature change was 7.5 Kelvin. So 0.2, which is given here, divided by 7.5, gives you a percentage uncertainty of 2.67%, or some of you wrote 3%, whichever. This is what the mark scheme says, but it's fine either way. Sometimes this is called relative uncertainty, and that's written, if you've done relative uncertainty, it's not written as a percentage, it's 0.0267. It's either way, you can do that either way. You then have to work out what the absolute uncertainty would be for delta H. Now, delta H we worked out in a previous question. Just remind you, put it up there. Delta H we worked out as 160 kilojoules, didn't we, per mole? 160 kilojoules. And so what's 2.67% of 160? That's your answer. Okay, so because I've got the mark scheme in front of me, I'll use the 3%, which they're using, rather than 2.67, but the method's exactly the same. So 3 times 160 divided by 100 will give you the answer, and that is 5 kilojoules, or 5 kilojoules per mole. Okay. Because of choices of how you round this and so on, there's a range of allowed answers from 4.1 to 5.5 kilojoules. Right, sketch a graph showing the concentration, how the concentration of iron sulfate changes. This is surprisingly poorly answered, really, given it's a pretty straightforward concept, I think. We are producing iron sulfate during the course of this reaction. This is a product, so it's going to start at 0, isn't it? And some of you started with it up here somewhere, which is a bit surprising. And hopefully you know that reactions at the start tend to be quite fast, and so the gradient's going to be steep, and they slow down during the course of the reaction, because the concentration of the reactants reduces. So they start fast and gradually tail off, and eventually might come to a halt like that. Be really careful that some of you kind of did this a bit sloppily, and I was fairly generous with marking it, but some of you had it drop away at the end there because you were sort of rushing it. This will probably lose a mark in the exam because you can't reduce the concentration over time. So be careful that just through kind of a little bit of sloppiness with writing the exam paper, that the concentration doesn't decrease at the end there. So you get 1 mark for having it go up the whole way along, and you get 1 mark for having the curve diminishing, or the gradient diminishing. The next thing, all you have to do is to say how you determine the rate of reaction. Now you need to use the right language here, and I'll try to be generous with the marking, but you should have said draw a tangent at time equals 0. So I'm going to draw it to show you what that looks like in case you don't know, but you draw a tangent at time equals 0, it would look something like that, with the line, the tangent, following along the gradient of the curve for as long as possible, starting at 0. So you get 1 mark for saying tangent, and don't use words like at the start. What do you mean by that? So the tangent at time equals 0 seconds. That's what you need to say, really. And then just some of you explained how you calculate the gradient, which was nice, but all you have to do is say calculate the gradient of the slope, or calculate the gradient of the tangent, and that's the rate in moles per decimeter cubed per second. And then you have to explain why replacing iron powder with a piece of iron. So you start with iron powder, you change to iron of the same mass, a lump of iron. Then it tells you it slows down the rate of reaction. Many of you didn't help yourselves because you started talking about why the powder is a faster rate of reaction. Answer the question directly, read the question, answer what it's asking you to do. So honestly, I can't remember the right Dr. Mark for that or not, but you should have been clear with why going to a lump of iron was slower, not why powder is faster. Answer it directly. Now you all know the answer to this, that the surface area decreases when you move from a powder to a lump. Straightforward. So just say that. Then talk about surface area to volume ratio. Talk about surface area. Surface area to volume ratio is why things might be cool down quicker if they're very small. But just surface area goes down. And if you, and again, year 10 stuff, if you've got and standard level rates of reaction, if you've got a reduced surface area, you reduce the frequency of collisions. You'd write that fully, but you know that stuff. Some people talking about activation energy, some people talking about energy of collisions, frequency of successful collisions. Just stick to the frequency of collisions, or the collisions per second. That's what's going on. There's a question here about electrolysis of iron sulfate using platinum electrodes, and we'll come to this later in the year when we look at electrolysis and look at the second half of the sort of high-level redox topic. But you need to show how oxygen is produced. I'm just going to stick down the answer here for future reference. Whoops, trying not to get it wrong. That's what goes on at the anode. So oxidation at the anode, water's being oxidized, is slightly different to what we teach you at GCSE, and at the cathode we say that the water is being reduced, and you produce hydrogen and 2 hydroxides. Okay, that'll do. I'm not even going to bother to go into that in any more detail now. That's that one done. I'm going to keep going to question 2. Empirical formula is one that the year 12s often struggle with, and it comes up an awful lot. So it's really worth getting your head around how you should tackle a question like this. You're asked to work out the empirical formula. You're told that it's carbon and hydrogen and oxygen. And so the first thing I would do is write down the data, which is what I told you. We've been given percentage data. Sometimes you're given mass data, and that works just as well. Works exactly the same way, but you write down the percentage of each of them. 62.02, 10.43 hydrogen, and you can work out then how much oxygen there is as a percentage by doing 100 take away that, which apparently comes to 27.55, and then you write down underneath that the formula, also the atomic mass of those elements. So 12 for carbon, 12.01, 1.01 for hydrogen, and 16 for oxygen. And that gives you, doesn't technically give you the moles unless it was mass here, but it gives you the molar ratios of them. And so the values you've got there are how many moles you would have in a 100 grams sample. So the N in a 100 gram sample would be 5.164, 10.33, and 1.722. Just do divided by each time to show what we're doing. Then you divide them all by the smallest, and you end up with 1. So you divide the smallest one of these three numbers is this one. So to work out a ratio, you divide them all by the smallest one in that set of 3. Divide that by itself, you get 1. Divide that by that, you get 6. And divide that by that, you get 3. So the ratio is 3 carbons, 6 hydrogens, and 1 oxygen. So the empirical formula is C3H6O. And you do need to give the empirical formula to get the mark there. We haven't done much on IR yet at all, but the interesting things about IR typically are the wave numbers to the left of 1500, and the interesting one here is this one, as you'll come to learn pretty soon. Deduce the functional group of the compound. If it's got one of those things there, big old fat peak at 1700, we know that it contains C double bond O, which we can say is a carbonyl. More on that later on. You have to say which functional group. So this functional group is carbonyl. It's not an aldehyde. It's not a ketone necessarily. You don't know which one of those things it is. It's a carbonyl. Okay. More on that later. And the relative molecular mass. To work out that, we look at the peak furthest to the right hand side, the greatest M over Z, which is 58 over here. So that's that one there. So you'll soon learn that the molecular ion is the peak furthest to the right hand side. So M over Z is equal to the molecular ion, which is 58. And the compound could not be oxidized using potassium dichromate. This is something we have looked at already in year 12. We know that potassium dichromate can oxidize primary alcohols. This isn't an alcohol, so it can't be that. It can oxidize secondary alcohols. This isn't a secondary alcohol, so it can't be that. And it can oxidize aldehydes. But this could not be oxidized with potassium dichromate, so it must have been, given it's got a carbonyl, it must have been a ketone. We're told it's C3H6O, and it's got a molecular formula of 58, so we can work out very straightforwardly that it's this substance here. And if you're struggling with a question like that when you come to looking back at these later on, the trick is to draw as many compounds as you can that have the molecular formula, and the empirical formula and the molecular formula must be the same because this has got a mass of 58. How many compounds can you draw with that arrangement of atoms? Well, hardly any. One of them is this. It had to be something like that because it's got a carbonyl. A carbonyl, as you know, is a C double bond O, and so this is really the only option. Well, it is the only option that can't be oxidized with potassium dichromate. The only other one you might have drawn that has a carbonyl would have been this one, which I'm drawing upside down for some reason. Something like that. So this aldehyde here, so that could have been oxidized, but it wasn't that one. Right, moving on to question 3. I'm going to take a pause here and do a new video.